You've probably driven past a rail yard at night and noticed something strange. Long rows of locomotives, all parked, all rumbling, diesel exhaust drifting up into the dark. They're not moving. They're not pulling anything. They're just sitting there, burning fuel hour after hour with nobody inside. Why does a parked locomotive need its engine running? Isn't this costing someone a fortune? Is it even legal? And what actually happens if they just shut it off? The answer isn't negligence. It isn't habit. It isn't some railroad company too distracted to flip a switch. It's physics, money, and an engineering compromise that's been baked into the North American railroad industry for 70 years. But the real reason goes a lot deeper than anyone standing outside that fence would ever guess. And once you understand it, you'll never hear that 2 a.m. rumble the same way again. Here's the thing most people miss. A diesel locomotive isn't just a big engine on rails. It's a mobile power plant, a compressed air factory, and a machine that's doing several critical jobs simultaneously, even when it isn't moving an inch. And the first job, the one that makes shutdown genuinely dangerous, has nothing to do with the engine itself. It's the brakes. Every car on a freight train uses an air brake system. The compressed air that operates those brakes comes from the locomotive, not from a separate tank, not from a backup system. From the locomotive continuously, through brake lines running the entire length of the train. That's federal safety regulation, not optional equipment, not a preference. A legal requirement that the brake system maintains operational pressure before any train moves. Here's where the math gets brutal. A fully loaded freight train can stretch over a mile long, 100 cars or more, each one connected to that same brake line. When a locomotive shuts down overnight, air pressure in that system starts dropping. Rebuilding pressure through a mile of connected cars isn't fast. It takes 3 to 4 hours to bring a fully depleted system back to operational levels. So think about what that means in practice. A crew shows up at 5 a.m. ready to move a train. Locomotive was shut down overnight. Brake system is depleted. That train is going nowhere for the next 3 to 4 hours while pressure rebuilds. In a rail network built around precision scheduling, where a delayed train creates a cascade of problems across hundreds of miles of track. A 3-hour delay before the day even starts is operationally catastrophic. Keeping the engine running keeps the compressor running, keeps the brake system pressurized, keeps the train ready to move the moment a crew climbs in. That's not laziness. That's the difference between a railroad that runs on schedule and one that doesn't. But the brake system is just the first reason. The engine itself has very specific feelings about being shut off in the cold. Here's where people get it wrong. The common reaction is just restart it in the morning. That's what works for a car. Turn the key, engine fires, you're moving in 30 seconds. But a diesel locomotive isn't a Honda Civic. Not even close. And the difference matters enormously when the temperature outside is minus 20 degrees. Diesel engines don't use spark plugs. They use compression ignition. Squeezing air so hard it heats up enough to ignite fuel on contact. That process depends entirely on the engine already being warm. A cold start in freezing temperatures means incomplete combustion, excessive smoke, and serious wear on cylinder walls before the oil has even circulated properly through the system. A practice widely understood among railroad maintenance crews, though exact figures are debated, is that a cold start below freezing puts wear on a locomotive engine equivalent to several hundred miles of normal operation. That's an entire day's worth of revenue service extracted from the engine before it even leaves the yard. But engine wear is actually the secondary concern. Here's the first. Locomotives carry between 200 and 400 gallons of coolant. Not the 1 or 2 gallons in your car. Industrial volumes. And even with antifreeze mixed in, extreme cold has limits. In severe enough temperatures, coolant can gel, thicken, and in the worst cases, freeze solid inside the engine block. A cracked engine block on a locomotive isn't a bad week. It's a $50,000 to $200,000 repair. The locomotive comes out of service for weeks. The idle keeps coolant circulating, keeps the engine above freezing, keeps the machine alive in a very literal sense. Then there's the third layer. Locomotives use massive industrial battery banks to start the engine and power onboard systems. In sub-zero temperatures, battery capacity drops dramatically. A locomotive that sits cold overnight without the engine running to recharge those batteries may simply not have enough power to restart in the morning. Dead engine, dead brakes, dead train. So now you have three interlocking problems: brake pressure, engine damage, dead batteries. And then there's the law. Here's where it gets interesting. Anti-idling regulations exist across North America. Emissions rules, noise ordinances, environmental standards pushed through by communities living near freight corridors. But written into those same regulations are explicit operational exceptions for exactly the situations we just described. Freezing temperatures that risk engine or coolant damage, brake system pressure, maintenance, battery charging for reliable restart. The locomotive idle overnight isn't violating the law. It's following one law while legally navigating an exception carved into another. One parked locomotive, two sets of rules, both applying at the same time. And here's the part that sharpens the picture. Not all locomotives face this equally. Switcher locomotives working mild climates, the ones doing short yard work and returning to heated maintenance facilities every night, can shut down safely, park, lock, walk away. But long-haul road locomotives operating through Montana in January or Northern Ontario in February live a completely different reality. That engine running overnight is the difference between a train that moves in the morning and a train that sits dead on the tracks for half a day. The solution the rail industry developed is called an auxiliary power unit, an APU. A small diesel generator mounted directly onto the locomotive, roughly the size of an industrial air conditioner. It runs the electrical systems, maintains battery charge, keeps critical components warm without firing up the main engine at all. Cleaner, more efficient, smarter engineering. But here's the catch. An APU installation costs between $150,000 and $300,000 per locomotive. That's a generator system that costs as much as a house. Smaller regional railroads operating on thin margins simply cannot absorb that capital expense across an entire fleet. Shore power exists too. Industrial electrical outlets at rail yards that let locomotives plug in and draw grid power instead of burning diesel. But shore power only works where the infrastructure has already been built. A long-haul locomotive stops wherever the crew's hours run out, often in the middle of nowhere near a hookup, so the main engine keeps running. The math is brutal, and to understand why the habit runs so deep, you have to go back 70 years. This is the part everyone misses. Locomotive idling hasn't always looked like this. Go back to the steam era, and the problem didn't exist. Steam locomotives never had a cold start issue. The firebox stayed warm as long as there was coal and water. Crews would bank the fire overnight, keep a low burn going, and the locomotive was ready to move in the morning. Simple, reliable, no battery concerns, no compressed air anxiety. But then, dieselization swept through North American railroads in the 1950s and 60s. Diesel locomotives were more efficient, needed smaller crews, required less maintenance, and could cover far greater distances without stopping. Railroads converted fast. But diesel engines introduced a problem steam never had: cold starts. Early diesel locomotive engines were genuinely brutal about it. Engines that wouldn't turn over in January, coolant that froze solid overnight, battery banks that died before dawn. The solution was immediate and obvious: leave them running. It became standard operating procedure taught to every new maintenance crew, written into every yard manual. baked deep into railroad culture across the entire continent. And here's the problem with deeply baked habits. They outlast the original severity. Modern locomotives have better cold start systems, synthetic oils that flow properly at low temperatures, improved battery technology, automatic shutdown systems that monitor conditions and restart the engine when needed. The engineering has genuinely improved, but the behavior stayed. Partly because some of the risk is still real. Partly because changing fleet-wide operating procedures across an industry this large requires enormous institutional will. And partly because the line between what's still necessary and what's now just habit isn't always clear, even to the people running the railroads. Some of that overnight rumble is pure engineering necessity. Some of it is 70 years of momentum. Telling them apart is harder than it sounds. Here's the surprise. You've been touching this system your whole life without knowing it. That bowl of cereal you had this morning, the grain inside it rode in a hopper car behind a locomotive that idled overnight at a terminal in Kansas or Nebraska. The lumber framing your house, rail delivery. The steel in your car, rail delivery. The fertilizer that grew every vegetable in your refrigerator moved through winter behind locomotives that stayed running in the cold. That distant train horn you hear at 2 in the morning from your bedroom. That's a locomotive about to idle for hours at the next crew change point, keeping brake pressure alive, keeping batteries charged, keeping the system ready to move again at dawn. Now for the real trade-off. Diesel exhaust from idling locomotives isn't nothing. Particulate matter and nitrogen oxides drift into neighborhoods built along freight corridors. That's a legitimate concern, and communities near those yards have every right to push for cleaner solutions. A fleet of 500 locomotives idling 8 hours a night burns thousands of gallons of diesel, going absolutely nowhere. The numbers are hard to ignore, but here's the context that rarely gets mentioned. Rail freight is 3 to 4 times more fuel efficient per ton mile than trucking. Moving that same cargo by road would burn dramatically more fuel and produce far more emissions overall. The idling problem is real. The alternative is worse. The good news is the industry is genuinely changing. Tier 4 EPA emission standards pushed manufacturers toward cleaner engines. Automatic shutdown systems now monitor temperature, battery charge, and brake pressure simultaneously, cutting the engine when conditions safely allow. Hybrid locomotives with large battery packs are entering service. Shore power networks are expanding. The idling habit is shrinking, just not as fast as anyone would like. So here's where you land. You drove past that rail yard thinking you were looking at waste, negligence, a bad habit nobody bothered to fix. But what you were actually looking at was a brake system that takes 4 hours to rebuild from zero. Diesel engine physics that turn a cold start into mechanical trauma. 200 gallons of coolant that can freeze solid and crack an engine block worth $200,000. Industrial battery banks that die overnight in sub-zero temperatures. A regulatory framework with explicit exceptions written specifically for these engineering realities. And a 70-year-old operating habit with very logical roots that the industry is still slowly unwinding. That low rumble echoing across the yard at 2 in the morning isn't carelessness. It isn't a railroad company too distracted to care about fuel costs. It's the sound of brake lines staying pressurized, coolant staying warm, batteries staying charged, a machine staying ready. It's the hum of the system that moved the grain in your cereal, the lumber in your walls, and the fuel in your tank. And if you think locomotives are complicated, wait until we get into why railroads still use air brakes, a technology invented in 1872 that nobody has managed to replace.